record you now. Thanks.
Okay. Well, thanks for the rather kind and exaggerated introduction there, Dave. First, like to acknowledge all the people that, well, you people being here, yet another Zoom call. And to thank some people who have influenced me over the years, and you can see them listed there at the bottom in chronological order. They might be horrified at some of the things I'm about to say, but nevertheless, they've been very important to me as a sounding board for some ideas over the years. I think all of us have had this experience. You go to an outcrop, you look down and you say, just what on earth is going on here? And this talk starts with that sort of curiosity and a hunch, no more than a hunch, that if get an explanation for this, it might be fundamentally important into processes. It turns out that this sort of view is typical of these Appinite complexes, which have very simple mineralogy. About 99% of what you're looking at there are just two minerals, hornblende and plagioclase. Yet the textures, as you see, are just wildly varying.
Oh, Brendan, I'm going to ask you to turn off your video part and just continue on, just to make it so you're less breaking up.
All right, so where am I turning off my video? I used to be able to do that pretty easy. I may have to go out into a different mode here for a second. Oh, stop video. I'm being stupid here. Here we go. That better? Okay, I think I've turned off my video. Okay, so as I say that 99% of this mineralogy is hornblende and plagioclase, but the textures are widely varying. And as you know, hornblende is a mineral that accepts water into its crystal structure. And water is sort of a common theme of this talk. You can see here, this is another picture of an outcrop or part of an outcrop of Appinites. And you can see again, it's dominated by hornblende and plagioclase. And you can see these rather pegmatitic textures here and sequential sort of tree-link type growth. So we know that water is a fundamental variable in magma chemistry and textures as well. And we also know there's been a plethora of laboratory experiments and theoretical considerations about the properties of water and what they do to magmas. But in Appinite complexes, we have it revealed by nature itself. And so there's a lot of instruction we can do, but we can gain by looking at these complexes in that sense. So one of the things about Appinites, they may be small, but just like leprechauns, they may be small, but they're very significant. Almost always, they're adjacent to large granitoid batholiths. And so part of the talk is going to be trying to generate a connection between these two processes. And also what it tells us about magma plumbing systems in general. Now, most introductory texts gives our students a rather simplistic view of what magma chambers look at, this sort of blobby sort of diagram that you can see here. And so, as you know, our students probably anticipate from this that if we ever get an erosional level down to expose this batholith, that there'd be one large blob, and it usually is represented as one large blob on a map. But I like this diagram, this cartoon of Donnelly's here, where he's envisaging some of the dynamics that goes on within a magma chamber and its emplacement. We now know that magma chambers are really very complex, that there are multiple injections from a lower crustal zone known as a mash zone, where there's melting, assimilation, and a lot of hybridization going on. And we've got evidence of this sort of multiple incremental emplacement of these magmas. Often from things like zircons, which are brilliant recorders of these processes in the autocrysts, which may record emplacement, in the anticrysts, which may record magma gestation time, if you like, before emplacement, and in xenocrysts, of course, incorporated from the wall rock. But if these magmas are compositionally homogeneous, these increments may be very hard to recognize in the field. However,
sorry. some people were not able to see your diagram, so and other people are. So it may be an issue between a phone and a visual. So if you could just, yeah, we'll just go with you show with your video on after all, so that they can see those. Sorry about that.
Okay, with the video on. Okay.
You were,
right.
You were
Is
clear.
that on now? Okay. All right. So there may be a bit of a trade-off here. I'm in a rural community with sort of storage Wi-Fi. We'll do what we can. Okay. So say that in this sort of dynamic process where a lot of magma emplacement is in feeding these batholiths, if these magmas are relatively homogeneous, then you might not get much visible evidence of these emplacement processes. But appinites are anything but homogeneous, as you can see from the pictures I showed you above, and so they may preserve visible evidence of these processes preferably. So I've given you sort of by way of preamble what the potential significance of these small little complexes are. Just what I'm going to do next is go to the type area, Appin in Scotland, where appinites were defined, and just give you their general features, what is inferred to be their tectonic setting in that area. Then I'm going to zoom back into Nova Scotia to the appinite body I know best, the Greendale complex, and look at the relationship between magmatism and its tectonic setting. And then what we can gain from that about petrological constraints. And then you're going to really think, if you haven't thought so before, you're going to really think I've lost my mind when I get this into a sort of one outcrop into one complex. And then to tell you that in fact it is a small, I think anyway, a small part of what is in fact a global signal. So on to type area. Appinites were originally defined in the Scottish Caledonides more than a century ago. And you can see in red are the batholiths, in black are these little dots of appinite complexes, which actually sort of overstate really some of the size of these. And if you zoom in and to be here into the Appin district in the Caledonides, some of you may recognize some of these whiskey type names, and maybe that's one of the reasons perhaps for some of the complexities in the literature, I don't know. But so you can see in black these appinite bodies, they're tiny if you look at the scale in here, relative to the size of the classic Caledonian batholiths. They originally defined by Iliamov in 1916, and were recognized, coeval ones recognized in the Irish equivalents in the Caledonides, associated with the Donegal composite batholith suite. They're really around one particular batholith within that suite. They're generally associated with large granitoid batholiths. They're preferentially associated also with major faults. As you can see in B here, the appinites in the Appinite district are right up along the Great Glen Fault, and the appinites near Loch Lomond, to the south of Loch Lomond, are on strands, if you like, or splays of the Highland Boundary Fault. Also, and particularly this might be very important for those of you who are interested in the lamprifiers or the South Mountain batholith, for example, they were also defined as the plutonic equivalent of lamprifiers. So it's possible that some of the things I'm talking about today, relationship of mafic and felsic magmas, may pertain to some of the South Mountain magmas as well. So on the basis of these studies, it was well recognized that appinite complexes are coeval plutonic and hypabyssal rocks being the lamprifiers. But even inside these small little plutons, there are actually multiple dikes. There may be blobs on a map, but there's a lot of internal division in them. They range from ultramafic to felsic in composition, so the whole spectrum of igneous petrology, really. Oh, sorry. Hornblende is the dominant mineral, as I discussed before. A lot of evidence is a very water-rich system, pegmatitic textures and the like. Lots of evidence for mixing and mingling of magmas, of coeval magmas of different compositions. It's a juicy system, so there's a lot of evidence of host rock contamination. I'd say water is an important theme here. And in some region in Scotland, they recognize what they call these explosion breccias, local pipes where they think the fluid pressure is enough to hydraulically fracture and brecciate the overlying country rock. Now, appinites, as you could tell from some of those slides, really are a textural term. And they escaped IUGS classification, probably because they were small and not worked on very extensively. But if you had to classify them, just so you see them compositionally, the ultramafics, olivine, hornblende, pyroxene diagram, you can see them plotting towards the hornblende apex, as you might imagine, olivine, hornblendes and the like, hornblendites. If you look at the sort of mafic end members, there's their hornblende gabbros or pyroxene hornblende gabbros, that sort of thing. Intriguing, if you look at the felsic end members, I guess they are, there's two different sort of suites depending on where you are. In some associations, they're sort of bog standard calc-alkaline compositions. But rather intriguingly, in other associations, there are these barium strontium granites. This is what they're called in the caledonites. But in fact, they're compositionally indistinguishable from adikites and TTT suites. And so I've seen references to Archean, late Archean appinites associated with TTT suites and adikitic compositions. Despite the fact that the mineralogy is dominated by hornblende and plagioclase, except for the ultramafics, the chemistry is quite variable. Even among coeval appinites. In the Scottish caledonites, it tends to follow this sort of shoshonitic trend in major elements, but also in rare earths and trace elements. You can see in the lower diagram here that the Scottish caledonites are strongly light rare earth enriched, like shoshonitic type tendencies. On the other hand, the Donegal, and these are the same age, they tend to be calc-alkaline, normal calc-alkaline, and have this light rare earth enrichment, the moderate light rare earth enrichment. One of the impressive studies in the Scottish caledonites by Mike Fowler and colleagues, he showed, if you look at the upper right here, that for compositions that vary from gabbro to granite, so the appinite complexes themselves and the coeval granites, that they follow in this parallel trend. And Mike interpreted that to reflect that the felsic rocks, the batholiths, were actually derived from the mafic, from the appinitic mafic parents by crystal fractionation. Now, if you look at the map on the left-hand side, you'd say to yourself, wait a minute now, the granitoid rocks are very voluminous, but the appinites are sparse at best. And so this is the importance of Donnelly's little cartoon here, potentially. This is sort of a spoiler alert, if you like, is that this may be our erosional level you see with the dashed line with the granitoid batholiths. The appinites in green may be spatially preferentially located around the faults that bound the system, but they may be genetically connected to the processes going on beneath the granitoid batholiths themselves. So more about that a little bit later. Now, the few relationships showed that these barium strontium granites were in place after the bulk of the deformation, so in extensional to post-orogenic collapse setting. So we're dealing with events towards the end of subduction and collision in the Scottish caledonites, and more about that now. So if you look at independent work, looking at the tectonic scenario of the appinites in their type area, this is the choose model, but it's very like it. They are based on a wealth of studies on structure, metamorphism, ages of magmatism that build up the evolution of this margin. And the early history of it is very much like what we know of in the Appalachians, with subduction away from the continental margin, oceanic arc, which the continental margin is to collide with, subduction polarity. This is our equivalent of the tectonics right in here. And eventually, subduction hauls in Baltica and Perigondwanan terrains. and closes the Appinite Ocean. And the Appinites, the age of the Appinites tells us they're in place at the time of this sort of regional setting. About the time of the cessation of subduction, of collision, closure of the Appinite Ocean. And on the basis of that, Atherton and Garney, almost 20 years ago now, maintained that the granitoid rocks were probably related to a stenospheric upwelling in the aftermath of slab breakoff, or if you prefer, slab failure. Since that time, we actually have, thanks to Bob Hildebrand and Joe Whalen, discrimination diagrams that can actually test and see whether the granitoid compositions do agree with that. And yes, indeed, they occur in the slab failure field. So this is telling us that the granitoid rocks and the coeval appinites are in place in this sort of late subduction to collisional to post-collisional setting in which there could be a stenospheric upwelling. Now, I've seen this sort of model employed in many other regions. And this is just one example. This is from the boundary between Tarim and Tibet. And you can see in this, their model in here of Ye et al. Essentially, they're invoking the closure of an ocean by subduction. And the Appinites and the coeval granitoid rocks are in place at the time of subduction cessation and time of collision. And they invoke a stenospheric upwelling as a thermal trigger of some of these processes. In fact, I've seen studies, papers written on late Archean examples of appinites and coeval granitoid rocks, and using this model to infer that plate tectonic processes must have existed in the late Archean. So, these sort of associations don't really answer some fundamental questions. They provide us with some great constraints. But how does this tectonic setting actually influence magma petrogenesis? How do these tectonic scenarios translate into getting us the igneous compositions that we do get? How do they account for magma compositions, the diversity of textures that we're seeing? What is the genetic relationship between the appinites and the batholites? And is there potential to get a window into the mantle processes that may be triggering the magmatism in the first place? Do appinites contain this sort of record? And from that, can we track the sequential and incremental emplacement of magmas that may yield these batholites and their satellite appinitic bodies? So I'm going to now to the appinite body I know the best in the Greendale complex in the northern part of the Antigonish Highlands. Georgia and David have described many equivalents within the Cobbergwyd Highlands as well. And there's several papers they've written, if interested, they're very easy to find. So switching to the Antigonish Highlands, like the Scottish Caledonides, thanks to recent dates in White et al. That's coming out CJS next month or so, we now know that the appinites, the Greendale complex that you see here in this, at least on my screen it's purpley color, are indeed coeval with some granitoid batholites within the Antigonish Highlands itself. So that same sort of relationship with the Scottish Caledonides is there. If we zoom in on the northern Antigonish Highlands, you can see that it's located between the Hollow and Greendale faults. The Greendale fault is not very well exposed, but the Hollow fault is well exposed. And there's lots of evidence along the coastline here of coeval motion along the fault at the time in which the appinite was in place. More of that a little bit later. But that too is a similar sort of connection to the Scottish Caledonides. So the age of the Greendale complex, probably the best estimate of its age, comes from uranium lead titanite age of 607 plus or minus 2. But to give you an example of the dynamic setting in which this must have been placed in, the rocks in Trude have detrital zircons as young as 613 plus or minus 5. So this setting has to be one where a volcanic arc basin is being deformed almost as the sediments are being deposited. So it's a very dynamic, active system. Another study, just by way of giving you some context, on the wall rocks around the Greendale complex, using crystal chemical parameters in the wall rock, tells the depth of which the Greendale complex is exposed here is a depth equivalent to about 2 to 3 kilobars. Okay, so a lot of things are similar to the Scottish Caledonites, but there's one thing that's fundamentally different. And that is that most of the models for the end of Avalonian arc magmatism, the Greendale complex is within this Avalon terrain. That detail is not important really here. But most of the models for the end of magmatism are not related to collision at all. So that's very different from the Scottish Caledonites. And most of the models invoke some sort of end by the generation of a transform. How that became a transform is open to debate. But there's no evidence of regional deformation or regional metamorphism or any sort of major uplift and erosion or anything like that associated with collisions. Instead, most models for the end of magmatism is a generation of transform fault, perhaps analogous to the ridge trench collision and the generation of the San Andreas type system. If that has any merit, then the common denominator with the Scottish Caledonites would not be slab breakoff necessarily, because there was no collision to generate the breakoff. But behind these generating transforms is in fact generates a slab window, a hole in the slab, and through which the asthenosphere upwells. So in fact, perhaps the common denominator here are tectonic environments that generate asthenospheric upwelling. In the case of the Caledonites, slab breakoff. In the case of this region of the Avalon, a generation of a slab window by a generation of transform margin. Another common denominator, of course, is water availability. And we know that water in the magma depolymerizes the magma, and that facilitates the transport of ions, and that facilitates rapid growth of crystals. Nevertheless, the occurrence of mafic pegmatites, which is common in appinites, is actually not very common in mafic magmas in general. So simple mineralogy, but complex textures. So let's have a look at some of the lithologies in the Greendale complex. These are examples of the ultramafic rocks. These are the dark things that you're looking at in here. And early sheets of ultramafic rocks are sort of dismembered and stretched and deformed by later sheets. There are some coherent sheets as well. And oh, it's a little blurry, sorry, but these are olivines in thin sections surrounded, poikilically enclosed by hornblends. This is the typical textures that you might see in thin section. If you look at the more mafic compositions, those that go from gabbro to diorite, again, hornblende plagioclase, but the textures are absolutely wild. You can see this ring growth again, an oscillating growth, if that's the right term, between plagioclase and hornblende, and back again, and back and forth again. There's some plagioclase surrounded by hornblende, surrounded by plagioclase, surrounded by hornblende, and there are even little, you can get hints in here of sort of an oscillating hornblende plagioclase growth. If that wasn't enough variability, there's also felsic rocks which tend to be late. You can see some sharp contacts that are sort of quasi-planar. Some are sort of locally scalloped sort of contact relationships as well. They also occur in more brittle sort of environments. It looks sort of brittle, but when you get your eye in, you might look at these sort of dark regions in between the felsic compositions. Your eye can get sort of befuddled and think, well, maybe there's some stringers of felsic material in here as well. So the whole thing may be mingled, and in this case, it's mingled. There's a lot of evidence of coeval dynamic mingling between these compositions. And then there's other sorts of contact relationships as well, where we're dealing more with mixing the mingling. So we not only have mafic pegmatites, but we also have felsic equivalents as well. So as Alan often tells me, many answers are in the minerals. So heeding on that sort of call, we did a detailed analysis of the amphibole compositions to see what they would tell us. My rather crude depiction of an amphibole composition is something like this, where Z represents the tetrahedral sites, and you can see them down in this picture, these inwardly pointing tetrahedral sites, Z equals 8. Glued together by cations. Y equals 5, here are the 5 cation sites in here. These are the X equals 2. And A is a site that contains alkalis and can be vacant, but can also contain alkalis depending on the exchange vectors are in the solid solution series that we're looking at. So in the mafic rocks, and as I'm going to show you in the ultramafic rocks, they're compositionally almost identical. They are essentially chermakitic to magnesio-hornblende compositions. In other words, typical igneous hornblende compositions. And a hornblende or an amphibole we might expect in these low pressure situations, if it was metamorphic, would be an actinolytic composition. And you can see the same thing in the ultramafics, chermakitic to magnesio-hornblende compositions. If you look at to what solutions are controlling their composition, well, this in here is a Chermak substitution, where aluminum goes into the 6-fold and the 4-fold site. Along the x-axis here, this is an Edenite substitution, where aluminum entirely goes into the 4-fold tetrahedral site. And you can see that the solid solution is somewhere in between these two vectors, and dominated by Edenite substitution. And the way I explain this to myself, this may not be right, but the way I explain it to myself conceptually is that at these high igneous temperatures, there's enough energy to open up the tetrahedral sites, and so aluminum can go in 4-fold coordination. And for those of you who know, about blue schists and glaucophanes and the like, at those low temperature metamorphic sort of conditions, aluminum instead will go into 6-fold coordination because they can't get into the tetrahedral site. So you see the same thing in the ultramafic rocks. The point here is that from as far as the major elements are concerned, the amphiboles are indistinguishable, whether they're in the rocks of ultramafic composition or composition. This is a plot from Georgia and Davis' 2018 paper, where they show the range of aluminum compositions in hornblendes in the Greendale, but also in their equivalents within the Cobequid Highlands. And the Greendale data is shown in black in here. And you can see that what that infers are higher pressures, so 3 to 7 kilobars, than what Abel et al. Inferred for the ore. So the hornblendes crystallize at deeper levels than, many of them crystallize at deeper levels than their current erosional level, if you like. And that's sort of consistent with the textures. If you like, some of these hornblendes clearly crystallize in situ within the melt, those texture relationships, but some of them may well have crystallized deeper down and carried up in magma as it was in place along these fault systems. So some of the things you can do with these hornblendes is you can take their compositions from core to rim. And here's an example here of, you can see the rare earth compositions with a negative europium anomaly, telling us that plagioclase was on the liquidus while the hornblende grew. And if you look at the mafic rocks, the amphiboles in the mafic rocks, this is true by and large of all those amphiboles, a negative europium anomaly, telling us that almost certainly that plagioclase was on the liquidus co-precipitating with it. However, if you compare that with the ultramafics, you get a different signal. No europium anomaly. before plagioclase was on the liquidus, quite likely, telling us that these hornblends grew perhaps from the olivine pyroxene reaction relationship, but before hornblende was necessarily on the liquidus. So what does this tell us about conditions? Well, we all are familiar with the iconic Bones reaction series and the sequential crystallization of olivines, pyroxenes, and amphiboles. Well, if you add water to the system, those stability fields change. As you might expect, the stability field of hornblende increases with increasing water pressure. In contrast, the stability field of minerals like plagioclase and olivines and pyroxenes decrease. And so you get intersections between their stabilities, and at situations in here, high water pressures, for example, where hornblende will crystallize before olivine. And at certain pressures, olivines and hornblendes will crystallize before plagioclase, and other pressures, they'll be about the same. So this is telling us perhaps that if plagioclase is not on the liquidus for the ultramafic rocks, that the hornblends crystallize at pressures greater than 2.7 kilobars, whereas the ones with plagioclase on the liquidus are telling us that they crystallize at lower pressures. So some of the hornblends, at least, were transported up from depth, probably. Okay, so that tells us about compositions. What about fabrics? And you can see that there's not just textures, but the actual fabrics of the hornblends change. Their orientations are very different from one part to another. Now, I take students to this outcrop and I say to them, look at that perfect linear structure. And they look like I just come down from Mars. Whereas in fact, it is a perfect linear structure, but you can't see the lines, because what we're looking at are like the equivalent of cross sections of logs. So then after they have been scratching their head for a while, I tell them to go around the corner and look at the rest of the outcrop. And this is what they see. These hornblends are long linear features. And the reason why they look so perfect on this is because those hornblends, and indeed some of the plagioclases that they're enclosing, are going back at right angles into that rock face. So I call it stacked log amphiboles, so there's a good term for them. I'll express that in a minute. I can see that they're very important linear structures within the Appinite complex themselves. But as I showed you earlier, there's also planar structures. And dismembered planar structures, like I showed you with those ultramafics a little bit earlier. But if you look in detail at some of these planar structures, they actually also contain linear fabrics. So if you get your eye on this, you'll see, yes, there are the bounding planar features, but there's growth perpendicular to the walls. You can see here that there are planar structures. If you follow the cursor down, hopefully you can. There's a planar features going diagonally across the outcrop here. But at right angles to those planar features are these linear structures. And on a Eurogranite's field trip that Barry Clark organized several years ago, one of the participants came over to me and said, Brendan, there is a term for that. It's called comb layering. Well, as many of you probably know, I haven't been near a comb for decades, but this is about as close as been to any. So here's more comb layering, and you can see the layers and the linear features are at right angles to one another. I'm just showing this is sort of eye candy, same sort of relationship here and here. The felsics, many of the felsics are actually in conjugate sets, so they have a different sort of relationship. So how can we put this all together and explain these another structural feature. Many of us are, even though we may be igneous petrologists, we may be more familiar with pull-apart structures in sedimentary basins where sediments are supplied to basins. But you can actually see little pull-apart structures. Remember, the Hollow and Greendale faults were active, little accommodation spaces opening up for magmas that are invading the system. You see these sort of pull-apart structures as well. So how do we put this all together to explain the fabrics? Well, if in more circle sort of approach, if we have low deviatoric stresses, in other words, between sigma 1 and sigma 3, that the difference between them is low, and we increase the fluid pressure, and we know appinites and the magmas are rich in fluid, the Mohr circle migrates back towards the Mohr envelope and actually intersects in the negative field, and we end up with tensile fractures. However, at times where the deviatoric stress is high, with increasing fluid pressure, we roll back to the Mohr envelope, we intersect the Mohr envelope in the compressional field, in which case we end up with conjugate fractures. So several years ago, Andrew Hines, my thesis supervisor, and I put together this model to try and explain the orientation of this layering using evidence for coeval dextral motion along the bounding hollow fault. And this would be the orientation of the instantaneous strain ellipse that would be, two-dimensional strain ellipse that would be generated by this motion, where yellow would represent the plane of extension. If you imagine that, this blue arrow being pulled apart in the direction of sigma 3, it would open up extensional fractures in the orientation that you see here, sort of east-west. And the Riedel fractures, the conjugate shears, will be oriented like this. So I don't have time to go into the model. If you're looking for more detail, you can find it in that publication. But basically, the orientation of the layers, including the hornblende crystals that are oriented perpendicular to those layers, are consistent with dextral shear on the bounding faults. So the story so far, we've got water-rich mafic magma, dominated by hornblende and plagioclase, although there are multiple injections of compositionally diverse magma ranging from ultramafic, producing either ultramafic rocks to felsic rocks. They're in place along faults and fabrics. There is some feedback between magma emplacement and structure and the tectonic setting. And they're placed at the cessation of subduction, just as at the same time as that arc system was being converted into a transform fault. And so the appinites in this sort of context here, you can see in the Antigonish highlands and these coeval granitoid bodies, these are on the margins of the system, but they're potentially connected into mantle processes beneath them, which is what I'd like to explore coming up soon. So maybe these appinites are actually a window into the slab window that would occur behind the generation of that transform system. So there's a clear distinction in crystallization from the amphiboles, from the ultramafic and the mafic rocks, and evidence that hornblende crystallize at different depths. And so a BSc student, Ian Kaywood, for those of you who know Peter, this is Peter's son, Ian. We sent him some samples. Unfortunately, he wasn't able to get over here. We sent him some samples to do some oxygen isotopes on the hornblendes. And those of ultramafic composition have oxygen isotope values, plus 5, 6, et cetera, that are typical of mantle-derived water. Whereas the others, mafic to felsic compositions, show some evidence of interaction with the wall rock, hydrothermal, cycling and meteoric waters, etc. So at least some of the mantles, some of the amphiboles, the water in them has a mantle component, telling them there's some connection with mantle processes. So maybe this supports the concept that appinites, and by implication lamprifiers, which are the hyperviscally equivalent, provide windows into the mantle processes beneath the batholiths. And for those of you interested in the South Mountain batholith, that might be an interesting sort of approach to take. So what I've dealt with so far is a top-down approach. But to close the loop on this, you've got to have a bottom-up approach. And I don't have time to go into much detail, but the details are in this publication, Bill Collins et al. Came out last year. just to highlight a few things for if you're going through this paper. Most arc magmas rise on anhydrous or relatively water poor, and they rise and adiabatically erupt. So this would be sort of the equivalent of path A on this diagram. You see the temperature depth profiles in here. Appinites, on the other hand, may be things that are more equivalent to path C, the more hydrous arc magmas, that where magma is coming off this, it's been derived in the mantle. Maybe magmas are coming up to the lithosphere, asthenosphere boundary, start to cool to the geotherm. They exsolve this fluid phase that promotes rapid and extensive melting in the mantle lithosphere above. And if that water finds its way, or those melts find their way up to the base of the crust and maybe escape up towards the surface along these structures, then it's not surprising that some of the water in the appinites may have a mantle signature. So this is another diagram from that paper here, where during ongoing subduction, so as a precursor to this emplacement, as you know, there's a lot of hydrous fluid flux with water rising up into the mantle wedge above it, generating the mantle melts. And it's maybe these melts that are being generated that are coming to the base of the crust in here, and some of the representatives migrating up these bounding faults, in which case they may be connection to the heat system that's also generating the coeval granitoid batholiths. Now, so the next couple of slides, you're going to ask, oh, what on earth is the connection between the next couple of slides and these appinites? But just bear with me, and I'll try and show you how potentially this can be just a local representative of what is potentially a global signal. There is much debate in the literature about global tectonics about the time the Greendale complex was in place. What no one disputes is there is global scale Pan-African orogenesis. And see here in the brown shades in here, these orogenic belts that brought Gondwana together. Also, it's a time of not just a global scale magnetism, but of profound changes in all the Earth systems in the late Neoproterozoic. What is debated, the existence of Gondwana is not debated. What is debated is whether Gondwana was attached to Laurentia plus Baltica plus or minus Siberia at that time, in which case it's the entity we know as Pannotia. Some reconstructions show it, some don't. Here's an example of one that doesn't. Meredith et al. A few years ago, where you can see the blocks of Gondwana coming together, ultimately in their tightest pack at about 520. But that 520 is, that tightest packing is after the time in which Laurentia separated, in which case Gondwana didn't amalgamate for Laurentia separated in the generation of the Iapetus Ocean, in which case Pannotia in this case did not exist. Oops, sorry. And the reason why this controversy is debated at length in the literature over many decades is, although there's no dispute about the Pan-African collisions recording the amalgamation of Gondwana, many of those Pan-African collisions occur after the onset of Laurentia Baltica Amazonia rifting. Another problem we have is that paleomagnetic record at this time is ambiguous. There's all sorts of evidence for breakdown of the dipole field or also too significant true wander during the time period. And so there's a great debate as whether Pannotia, even if it existed, reached the 75% threshold to call it a supercontinent. And to give you an idea why that's important, and we'll get to the Greendale, and I'm getting to that in a minute, is that if Pannotia is not a supercontinent, then the previous supercontinent everyone agrees with, Rodinia, and the next one everyone agrees with, Pangaea, represents one supercontinent cycle. And this model here by Lee et al. Shows you that when a supercontinent breaks up, it generates these new interior oceans. So we go from A to B to C as it widens. If it continued to widen, like as if the modern Atlantic continued to widen and the Pacific continued to contract, we would skip E, would go straight to E, and we would have a new supercontinent with the previous ocean surrounding it, the internal oceans of one supercontinent around the next supercontinent. And this is an example of what we might call extroversion. As you can see, this model here pays Gondwana no heed whatsoever. It implies that Gondwana had absolutely no thermal legacy, had no imprint in the mantle at all. On the other hand, if you are maintain that Pannotia did exist, then the reconstructions are telling us that Yapta's ocean formed and its successor, the Rake Ocean, formed. But in contrast to the previous scenario, it's those very same oceans are the ones that preferentially subducted and closed to give us Pangaea, in which case we go from A to B to C to D, and Pangaea formed by introversion. So if Pannotia is not a supercontinent, Pangaea, the geodynamic models for Pangaea are one way. If it is a supercontinent, it's the opposite way. Extroversion versus introversion. So this becomes a controversy is, did the amalgamation of Gondwana impart a legacy in the mantle that must be factored into models of Pangaea? And if it did impart a legacy, how would you recognize it? So one way of conceptually viewing this, if this is the Pan-African orogenies in here, in these so-called interior origins, is that there must have been oceans in between them. You see in the cartoon on the right in here, with subduction zones. And this general zone of mantle downwelling would be in zones in which subduction zones would have accumulated and fired down to the core mantle boundary. And there's a whole bunch of processes go on there along the core mantle boundary by draping it that convert that downwelling into an upwelling. So if indeed Pannotia and Gondwana was a zone of mantle downwelling, that downwelling should have converted into an upwelling. And this is a Tanadel model showing you subduction zones along the core mantle boundary. And it should be okay, along the core mantle boundary. And these models telling us that when that happens, that blanketing effect generates plumes around the edges of the supercontinent. So with apologies to Tanadel, I've just cheated by putting Gondwana above that subduction zone boundary, because we know if they're Pan-African orogenies, those subduction zones must have been there. But Laurentia has no subduction zones within it and would be to the side. So one sort of test of this model, one test of this model is that if Gondwana and Pannotia had a thermal significance, we should be able to see plume-related magmatism around the side. I'm getting to Greendale, don't worry. But geodynamic models also tell us that if these plumes are rising, they don't get to surface uninhibited. They are actually very fickle. They get sidetracked and destroyed by barriers within the lithosphere, including subduction zones. Here's just an example here on the left, that here's a plume conduit ride. It impacts on subduction zone, and instead of going through the subduction zone, most of the plume material gets entrained and destroyed and dragged down the subduction zone. And so instead of going through the lithosphere, it gets entrained. The only places where it gets through the lithosphere are where there are flaws. And this is where the Greendale comes in, are where there are flaws and gaps within the subduction zone. So here's some various models in here. These relate to the Yellowstone situation, but they're analogous to what we're talking about. So in the model associated with the termination of magmatism, of Avalonian magmatism, and the generation of a transform, and the generation of a slab window, there is the hole in the subduction system that can allow the thermal response to the formation of Gondwana to come through. And that's where we'll preferentially see it. So if that's true, then, and you check the literature, the Greendale complex, its equivalents in the Cobblequids, are just one example of, and this is a sort of a literature survey of various places in the late Neoproterozoic and early Paleozoic where plume-related magmatism has been independently proposed, not in a global context, but just individual studies have proposed that there are plume magmatism. And so the Greendale complex is a tiny little outcrop, but it may be part of a global scale response to the formation of these Pan-African orogenies, plumes migrating preferentially up the sides of these supercontinents, and telling us something about the thermal disturbance associated with the amalgamation of Gondwana and portion of Panocha. To wrap up, and so we started here with just, gosh, what can I say, curiosity and a hunch. And so we can, I think, here's some of the first other things we can say, that Appinites are obviously water-rich magmas dominated by hornblende and plagioclase. They allow us to see and record multiple injections that comprise plutonic bodies. In the case of Appinites, we can see them because there are multiple injections of compositionally diverse magma. But if magmas were not positionally diverse, we may not see them at all. And so many red blobs on a map may in fact have internal divisions within them. I think that we can explain why they are satellites to large granitoid bodies. And those satellites bodies are preferentially in place along faults, which in fact is a connection to the mantle processes that are going on underneath and the processes that are going on that ultimately generate those large granite batholiths. They're in place at the cessation of subduction, and there appears to be evidence for strong mantle activity and thermal disturbance. Perhaps it's seen as ferrigot welling, but at least some Appinites contain mantle-derived water. So we may be getting a window into mantle processes and the origin of granites. And because we're transferring mass from the mantle to the crust, it may give us a window of how some of the crust is generated and connecting to arc activity in general. And so the Greendale expression may in fact be a Greendale complex may be a local expression of Gondwana's thermal legacy. And if so, the amalgamation of Gondwana should be factored into models for the origin of Pangaea and not just simply ignored. Thank you all for your attention. Hope you're still there.
Thank you very much. Very much appreciate that. Yeah, very clear. And we had quite a few people coming in a little bit late. So hopefully they were able to catch much of this. I did want to remind people that questions should go into the chat, and that as you ask questions, I'll ask you to unmute yourself and fire away at Brendan here. So far, Brendan, we don't have anybody in the chat. We're getting a few thanks right now, as we normally expect. And Deanne was the first one to thank you, just so you know.
So thank you very much.
And as you know, with most people, everybody is overwhelmed with talks related to Zoom and so on. So anyway, I can see people are fleeing now. But I do
myself in a minute.
I do have some questions coming in, and so what I'm going to do is forward those on to you. So, Dave Hollowell, you can unmute yourself and ask your question.
Hi, Brendan. Thanks for that.
Hi, Dave.
So, I haven't looked at too many Appinites, but one of the few that I have actually looked at is Strong Garb in Scotland, which has got carbonate and magmatic sulfides in. So question for you is, do you see magmatic carbonate and sulfide in Appinites in general, or is that one that I've looked at a bit of an anomaly?
Well, actually the Greendale certainly does have carbonates in them. I think I may even have a slide of it here somewhere. I took it out. Let me see. Just bear with me a second.
Yeah, sure.
And sulfides in those carbonates. Let me see. There we go. Right. So there are carbonates within the stratigraphy,
Mhm.
and so one of the intriguing aspects about this particular appenite is the competing role of CO2 in the fluid phase as well as water. And many years ago, I sort of surmised that perhaps that may result in differences in polymerization in the melt, and that may affect some of the compositions that we see. So, but this, I think in the case of the Greendale, I convinced myself, and maybe we'll have to discuss this, because I convinced myself that this was really the happenstance of it being in the wall rock.
Okay, yeah.
But maybe there's something more underlying about that. And I remember several years ago in the outcrop with Alan, he thought that some of these carbonates may be hydrothermal. And if that's the case, then that's perhaps something. If this is more common than I'd anticipated, perhaps that's something that should be investigated as part of the system itself. So, not answering the question, and I'm more or less opening up a possibility.
Yeah, all right then. Yeah, because that one that we did look at, which may be unusual, did seem to have mantle-like carbon isotopes in some of the calcite there. So rather than it being a wall rock thing. So yeah, that's.
Oh wow.
Yeah, but
that's interesting.
Looking around, it seems that this is maybe not normal for Appinite. So maybe there's something special about that one in particular.
Well, Donnelly and I looked at the Appinites in Donnelly Archipel, and I looked at the Appinites in Donegal, and we didn't see any relationship. Donnelly, correct me if I'm wrong there. But yeah. Well, that's something that maybe should be pursued. There's loads of things that should be pursued here. Lots of strings going in all sorts of different directions that need to be pursued. And I just recently retired from teaching, but I won't be able to do all these things, that's for sure. Can I ask you a question? Can I ask a question, David?
Yeah.
I assume that you're not located where that beautiful picture is behind you.
I am not. I am not out in Greenland right now. No.
Okay. Right.
No.
Lovely picture. Yeah.
No, I'm in the kids' playroom.
There.
Relegated like myself.
Yeah. Now we know that's the common one. Where we wish we were versus, and in essence, hiding the chaos. That
is precisely what it is. Precisely what it is. Yeah. Okay, thanks,
David. If you want to send me any literature on that, I'd appreciate it, and vice versa. I'll send you anything if you're interested in. I can send you.
Okay,
thank you, David. And, thanks, Brandon, for not answering all the questions and leaving it for some of those other guys like Dave and his group. Hamish, you're up here with a really good question. I was hoping somebody would ask that, so fire away.
Hi, Brendan. How you doing?
Hey, Hamish. How are you?
Very good, thank you. I did a bit of work in the Western Churchill on some lamplifiers. Most people know the ones from there as Manettes, but there's also a suite of Spessartites. And to me, these Appinites you're looking at look like Spessartites. So I'm just kind of envisaging what sort of mantle source you envisage for these mafic to ultramafic end members.
So that's another great question. Yeah, those associations have been made in the Scottish Caledonides as well. And when those guys were interpreting them as associated with lamplifiers, it was a composition. Well, the question, I can't give you a definitive answer on that, and perhaps the best exact reason why, it's sort of intriguing, is that in the Scottish Caledonides, the Appinite compositions are sort of shochenitic, and so are the lamplifiers. When you go to the Irish Caledonides and the lamplifiers and Appinites are coeval and coeval each other and the same age as the ones in the Scottish Caledonides, they're all bog standard calc-alkaline compositions. And so really, I think what this is telling us, and you know, I'm no expert on this, is that you know, the mantle was metasomatized differentially along its length. That depending on what material went down the subduction zone, and what the water was able to scavenge, what ions the water was able to scavenge, means that the mantle may be completely metasomatized. We have cal-cal compositions, but maybe differentially so. And so it may be telling us more about, you know, what was subducted, differences in what was subducted along the length of the R system. Feel free to come in with your own views on that.
Well, my only comment would be that, for instance, in the Western Churchill province, the monettes are coming out of a more potassic and also carbon-rich mantle source, whereas the spessartites are from obviously a water-rich. They look like your rocks are white and black, basically, right?
Right. Right.
So, but geochemically, they're almost identical.
Wow.
So it seems to be that the lack of CO2, they become water rich, maybe because its CO2 is blasted off into the upper crust earlier. And then they mingle and co-mix with granites, just as you showed.
Yeah, well, those processes aren't mutually exclusive, of course. So all those scenarios are plausible. Yeah, but it's intriguing that in the difference between, I find the difference between the Scottish and the Irish Caledonites Appinites and their coeval amplifier, particularly in not related to your question. I think that's something else that needs to be studied.
Okay, thanks. We do have actually Reg Wilson had, I think it was Reg Wilson had a question. Reg, just unmute yourself and ask away. Thanks, Hamish.
Hi,
Reg is
Brandon.
never muted, surely.
Hi, Brandon.
Hi, Reg. How you doing?
Great. Great talk. Very interested in scribbling down questions. I have only 3. I see someone else has popped in there before my last one, but at any rate, I'm interested in any connections with these types of rocks that may exist in New Brunswick. And first, I was wondering, and I have read your paper before on the 2013 paper.
Oh yeah.
And the broadly post subduction, but is there like a range of times after subduction ceases that you can expect to see or may see appinites?
They seem to be very time constrained. Let me just go back to the model here if I can. Gosh, I'm way down here. But let's see. The model in the Scottish Caledonites is analogous, I think, to what we would view when on the applications in a broad sense. Let me see, go back. Where was it? Sorry about whipping through here. Hope you're not getting too dizzy, guys. Oh yes, up here. There we go. You know, this is translatable to the appellations really. And so if you're talking of New Brunswick and, you know, where you could sniff them out, you'd imagine it would be this sort of age really. It would be the same as not same, but similar in age to the Scottish and Irish Caledonites. And, you know, at times when just after the slab breakoff, just after collision, it seems as though this potential asthenospheric upwelling is the additional energy that magmas need. They may, after they've been generated, to actually be placed along fault systems, and so obviously the proof is going out and going to the field and testing it and dating these things. But you would imagine that you could get them in this post very soon after late collisional or to post collisional setting.
I'll tell you why I ask. Two things. The last subduction in New Brunswick was over by the middle to late part of the Silurian, about 425 to between 425 and 420.
Mm.
And there is a igneous complex. Dave knows about it, and Dave, feel free to comment here when I finish. The Mount Elizabeth complex is cored by a roughly round granite, about 10 kilometers in diameter, and it's surrounded by a number of mafic phases, including some very coarse-grained gabbros that contain amphibole and pyroxene, apparently. And a small ultramafic pluton on the south side. On the north side, there's troctolites and related ultramafic phases, and there's amphibole-bearing alkalic granites on the west side that are a couple of million years younger. These are 417 to 415 years old. So several million years after we think the last subduction ended.
Yeah. Okay. Well, I'm going to just try to get out. Where is? Sorry for whipping forth here. This is Donnelly. I'm here. If the sort of relation we're envisaging, if these are sort of the Appinites at the level in which they're exposed in the Greendale complex, then I mean the levels of exposure are going to vary from one belt to another. So you saying that you've got mafic rocks surrounding a large felsic granitoid batholith. Well, okay,
they're
fair
scattered
enough.
all around. Some are small mafic phases are within the granite, but
Yeah, well, that's typical too. When you think about it, though, if a granitoid magma is getting in place and spreads out laterally, it more or less forms a rheological barrier to any more mafic rocks coming through the center, and the only place they can come through is on the sides. And so what you get within the batholith itself is a lot of mafic enclaves, which incorporate some of the earlier mafic magmatism. But after that, you can't get any subsequent mafic magmatism in the central part. All you can get is around the edges. So that's one variable. Another variable is, I would say, that if you've got a lot of olivines and things in there, you may be at a slightly deeper erosional level, maybe a little less water affecting the system. So there are variables in there, different flavors, but maybe the overall relationship is very similar.
It struck me when I read your paper that this might qualify, but it also struck me when I was reading that paper was it occurred to me that some of those rocks sound like they could be related to lamprifers. So when I saw lamprifers on your presentation today, I had to ask if there's what you think of a possible connection.
Well,
also,
I mean,
our lamprifers, as far as we know, are even younger than the mountain.
Well, I mean, lamprifers are from the type area. They're genetically related to Appinites. They are spatially associated with them. In Donegal, they're in exactly the same zones as the Appinites are in. In the Greendale complex, there are lamprifers. Those ultramafics are really lamprifers. They're inside the complex, though, right? And so, yeah, lamprifers are part of the scenario. And it's possible that in some complex, and I'm thinking here of the South Mountain batholith, that the lamprifers associated with the South Mountain batholith are sort of a different erosional type of level than what we're seeing in the Greendale complex. But really, they're telling us
all over northern New Brunswick.
Yeah, they're different parts of the same plumbing system, different erosional levels, potentially. I mean, it's just something worth
Brendan.
considering. Yeah.
Okay. Well, thanks, Reg. I'll let you jump in a little after when we go informal. We do have a question here from Zara. Yeah, just unmute yourself, Zara, and ask your question. We can elaborate on that a little bit too, maybe.
Okay. Hello, everybody. Brendan, thank you so
Hi,
much
Zara.
for the instructive talk.
Thank you. How are you doing?
Oh, thank you so much. I'm good. What about you?
Excellent. Excellent. Yeah.
Great. So I would like to ask a question about the economical importance of Appinites. So you said that it's possible to see this kind of rocks in the arc activity, right? In arc environment, during the arc activity.
Yes. Yeah.
And it is also, yeah, it is also has some mental signature, so it is affected from the mental.
Mm-hmm.
So what kind of temporal or and spatial relationship between appenite and porphyry copper deposit? Have you ever think about it?
I'm sure anyone who knows me knows that I'm way out of my comfort zone when it comes to porphyry copper deposits. But all I can argue is, all I can say is something just intuitive, if you like, or conceptual, and that is that these systems are very water rich. Water is flushing everywhere. The host rocks are bathed in water. So it's a very juicy system. And so everything that has the possibility of being transported, if it's soluble, will go. But the porphyry copper deposits, there's loads of other people on this, if the participants are still here, who could probably chime in on that. I'm afraid I'm not, I don't know much about them. If Alan is here, he'd probably tell you.
Yeah.
Sorry, that's
Well, I
David, of course.
I will give you my 2 cents worth, 5 cents maybe, depending. Is obviously I've been working a fair amount on cognate xenoliths and so on, but one of the classic examples is at Bingham. And Bingham has a lot of different magma systems injecting into it, different dikes into some of the core Pluton, as you know, there. And one of the things that was postulated early, and which is actually kind of known, is that to enhance metal transfer, as Brendan alluded to, but also sulfur transfer in order to achieve the right mass balance, to explain the saturation of massive amounts of copper. This was postulated by Jeff Keith, as well as Keiko Hattori, and other people have built on this in other areas. And so we do know that we have some alkalic igneous activity at that time, some of which verges on lamprophyres. The other component of that is also the same as that Brendan alluded to, and some people have postulated on, is that these types of magmas actually form the right tectonic environment, and also the advective heat you need to actually boost the porphyry into the right position of the crust to undergo catastrophic devolatilization, and in essence enhance single phase devolatilization over a large period of the crust, portion of the crust, in order to actually form one main episode that forms mineralization. So it's a combination of processes, and it's probably way more complicated than that even, but there is this association that we do see that you're absolutely right on.
Very interesting. So thanks for that, Dave. Thanks for your question.
Did you have any follow-up question related to that, Zara?
No, not this time. Thank you so much.
Well, thank you, and thank you for answering the question, Dave.
Well,
thanks, Zara.
Yeah, just the part that I know. Obviously, sure. I've worked a lot in Iran, and now I'm working in Turkey, which is why Zara joined us today. So we did have another talk, a question here that was related to. Obviously, we had some other questions that Reg had. We're gonna keep Reg on the back burner right now, and we have another David. Anyway, if talking about the Wycombe batholith. Anyway, I was just wondering if they wanted to unmute themselves and ask their question. The Walden batholith, anything?
I don't hear anything.
No, I don't. Anyway,
I can comment briefly on that, just because I don't know who asked the question, but that unfortunately was Trevor McCaddy's, or fortunately was Trevor McCaddy's Masters area. And I know, talking to him, that he described a lot of potassic granitoids in the Waffman batholith, and a lot of commingling textures with amphibole-rich mafic materials, basically. So I think that's maybe what David was talking about when he saw those.
Okay.
Yeah, I get the impression from many of your questions that and comments that these mafic satellites around granitoid batholiths are far more common and maybe not given all the attention that they need.
Yeah, well, actually, Hamish, you wanted to elaborate on the Cornubian batholith that you have a bit of experience with as well.
Yeah, sure. I mean, I haven't actually seen the Manets in Southwest England because I worked on other components there. But while working on my PhD material in southern Peru, which is also a very similar situation to the Cornubian batholith, you do see these in thick continental crust. Generally, you see S-type. And when I say S-type, I mean cordierite biotite bearing granites. And they almost always have shoshonitic lamprifiers, or, Manets verging towards spessartites. And they also have transitional lamproites associated with them, and shoshonitic basalts. Dan Contact worked in an area in southern Peru that was very similar to or in the same area I worked in. And you see these rocks around these larger batholiths all the time. And the key is when you get near the upper cupolas of these granitoids, that's where you really start to see more of the subvolcanic equivalents, and you can see the textures and the commingling and whatnot. You get deeper in the batholiths at a deeper exposure level, which Brendan was talking about earlier, and you just see these rounded micaceous xenoliths that you have no idea what they were. But they probably, a lot of them were probably potassic or even sodic, in some cases, lampriferic magmas.
Yeah, it would be really, that's interesting. It would be really intriguing to be able to get a better picture of how these mafic bodies vary down the length of the fault, if you like. And so that we get an idea of what to expect at these different structural levels. In the case of the Greendale, it's obviously a fairly high structural level. But perhaps one of the reasons why there's no magmatic or no volcanic equivalent is that if it was generated in these structural zones where essentially there's pull apart, there's one big pull apart structure, then any upward magma pressure is accommodated by movement along the fault, or vice versa, or feedback between them. And so there's no volcanic activity associated with it, because effectively you're in a pull apart zone. So this is loads of variables, and how these features might vary with depth would be an interesting thing to try and put together.
Yeah, okay, great. Thanks. I'm just going to stop recording here right now. I think